Dear student, now we will discuss about the electric potential. So first of all, what is the meaning of electric potential? Till now we have defined electric field. So what was the electric field actually? Electric field was nothing, it is the electrical effect of a charge. So electric field was that physical quantity in which we have defined the electrical effect of a charge in a vector form. Similarly, electric potential is also one of the physical quantity which explain the electrical effect of a charge, but this is not in a vector form, it is in scalar function. So we can say electric potential is the, so we can write about electric potential, it is representing electrical effect of a charge, electrical effect of charge in scalar function, and it is denoted by V. It is denoted by V. So how we are defining? There are certain points we have to remember. Electric potential or potential we are defining only for those type of field which are conservative, and for conservative field the absolute value we cannot define, always we are defining the difference in the value between 2 points. In the same way, electric potential, whenever we are defining electric potential, we are defining the potential difference between 2 points. So it is defined like, so electric potential or potential difference between 2 points, it is defined as the potential difference it is defined as the potential difference. So according to this, potential difference between 2 points is potential difference between 2 points is the change in potential energy per unit charge. Potential energy per unit charge. See the meaning of this statement. Suppose we want to see the electrical effect of this charge Q in vector form. We are defining electric field, but we want to see the electrical effect of this charge in scalar function, then we are defining electric potential. So suppose we want to see the potential difference between point 1 and 2. So what we will do, as per the definition, according to this, potential difference between 2 points is the change in potential energy per unit charge. So what we will do, we will put a certain test charge Q naught at position 1, then we will find the potential energy between Q and Q naught at position 1. After that we will put the charge Q naught at position 2, then we will find the potential energy between Q and Q naught at position 2. So difference of that potential energy per unit charge. So we can say V1 minus V2 is nothing, potential energy at position 1 minus potential energy at position 2 by Q naught, or in general we can write delta V is nothing delta U means change in potential energy per unit charge. In differential form, we can write dV is equal to your du by q naught. So, this is the fundamental relation for potential difference and potential energy. So, main point here we can write delta V is your delta U by q naught. This is the one very basic fundamental relation, and with the help of this we can convert in the other form also, or in differential form. Differential form is for a small change in the potential difference between 2 points. So, we would like to calculate what is the small change in the potential energy per unit charge. This is in the differential form. Now, how this relation can be expanded in the other form? See here, as we had defined, change in potential is nothing potential energy per unit charge, and in differential form we can write dV is your du by q naught. Now, this we can expand in the different form also. See, as we have defined earlier, the change in potential energy. The change in potential energy is nothing, it is the negative of the work done by electrostatic force. So, here also we can represent the change in potential energy in that form. Then we will see the very interesting result also and very good conclusion from that. As change in potential energy is equal to negative of work done by electrostatic force So, we can write du is minus F dot dr, where F is the electrostatic force. So, further we can write F is nothing charge, the force on test charge dot dr, this is your du. Then see the first and second relation. So, from first and second we can write dV is equal to here minus q naught E dot dr by q naught. So, this become your dV is equal to minus of E dot dr. This is very interesting and very useful result, and this can be said as a relation between potential and electric field. This gives relation between potential and electric field. Like this. And see from here, first point we can write negative sign in the expression. Negative sign in the expression tells us in the direction of electric field potential decreases. So, negative sign indicate in the direction of electric field electric field, potential decreases. Potential decreases. So we can say if the electric field direction is this, let this is the electric field direction, and if we are talking about any 2 points here, A and B, and let the potential of point A is VA and potential of point B is VB. So in the direction of electric field potential decreases, it means VB will be at lower potential as compared to potential at point A. So this is the meaning of negative sign. So this is the one very important result, and this we can further use in the different cases. See here. So now we got another relation between electric field versus potential. This is dV is equal to your minus E dot dr. So these are the all very fundamental and basic relation, and with the help of this relation we can determine so many results here. See, second point, let E is given as EXI cap plus EYJ cap plus EZK cap, and dr can be written as dxi cap plus dyj cap plus dzk cap. Then from here dv is nothing as E dot dr. So this further written as minus of EXI cap, EYJ cap, EZK cap, and dot product with our dr vector. So dxi cap, dyj cap plus dzk cap, and this gives us minus Ex dx Ey dy Ez dz like this. This is the dV value. Now if we want to find the potential between point 1 and 2, let point 1 means V1, point 2 means V2. So here we can integrate Ex dx, x coordinate of position 1 and then x coordinate of position 2. Similarly, y coordinate in position 1, y coordinate of position 2, and then z coordinate of position 1, z coordinate of position 2. In this manner, so that gives us potential difference between point 2 and 1 likewise. So this is the one conclusion we can draw. Similarly, in the third point we can say if potential is given as a function of x, y, z, let us dV is given as minus E dot dr, and if we want to find the electric field from here, so that gives us electric field is equal to minus of dV by dr, and here n cap gives us the direction of electric field. So this further can be written as minus of dV by dx I cap. A change in potential along x direction, that give you x component of velocity. Then rate of change of potential along y direction, that give you j component, and then dV by dz, that gives us K component of. So this is the relation by which we can get the electric field in the vector form, a potential given as a function of x, y, z, and this is the relation by which we can get the potential difference between 2 points if electric field given as a function of x, y, z. So this further we can use this relation in the next example. See, just like, so we can write here same relation. We can write dV is equal to your minus of Ex dx plus Ey dy and plus Ez dz. Similarly, this value we can write E is equal to here minus of dV by dx I cap dV by dy j cap plus dV by dz k cap. Now see one two example. From that we can get better idea about how to use this relation for potential and electric field. Let electric field vary according to the relation 2x I cap minus y j cap plus z square k cap. And now the question is this: to find the potential difference between point A have coordinate 1, 2, minus 1 and B having coordinate let 2, minus 1 and 1. This is the question. It means we have to calculate VB minus VA. Here electric field given as a function of x, y and z, and we want to find the potential of point B and A, so we can use this relation. See, dV, because electric field is variable, so we can use dV. dV is your minus of Ex dx plus Ey dy plus Ez dz. Now substitute the coefficient of electric field along x direction, that is 2x here, and Ey here minus y, Ez here z square. So then we can substitute here, value this 2x x dx minus y dy, Ez means here z square dz. Then simplify, integrate each and individual. So if this is your point A, so VA, and this is your point B, VB. VA means position vector of point A. A here 1, and then B position vector here 2. So 1 to 2, Y here 2 to minus 1, 2 to minus 1, Z is your minus 1 to plus 1. Now simplify. So VB minus VA is given as minus of x square limit 1 to 2 minus y square by 2 limit minus 2 to 1. Now then z cube by 3 and limit minus 1 to plus 1, like this. And after that we can simplify. So minus, this will be your 4 minus 1 3, and this is your 1 by 2, y square means 1 minus 4, and then this will be your 1 by 3, 1 minus 1, this one. Now simplify further, minus 3 here plus 3 by 2, and this will be your plus 2 by 3. Then we can simplify. So, this is the potential difference between point B and A. By simply we can use this relation. Similarly, if we want to find electric field, so see the another example. From that we can get the electric field if this is the format. See another example. The potential in a space is given as a function of x, y, z. Let potential is given as 2xy into z square. So find the electric field at point 1, 2, minus 1. So question is given here. The potential in a space is given as a function of x, y, z. It means potential at a point vary as x, y and z vary. So find the electric field at point 1, 2, minus 1. So here, if we want to find electric field, so we can write this expression. E is given as minus of dv by dx I cap dv by dy j cap plus dv by dz k cap. Now, potential function is given as 2xy z square. When we are differentiating with respect to x, keeping the y and z as constant, so here this relation become your 2yz square I cap plus keeping the y, x and z here constant, then it become your 2x z square j cap, and then it will be your plus 4 xyz k cap. So this is the value in terms of I, j, k cap vector. Now substitute the coordinate of that particular point where we have to find electric field. So these coordinates are 1, 2, minus 1. Substitute here. 2, y is your 2 and z is your minus 1. So minus 1, 1, 1 into 2, 2, 4. 4 I cap plus. Now this 2xz square. 2xz square will be your 2. 2j cap. Now here 4xyz. xyz will be your minus 2 and this is your 4, so minus 8 k cap. So finally, electric field at that particular point is given as minus 4 I cap plus minus 2j cap plus 8 k cap. So this is the solution of this particular problem. So in this manner, we can use this relation to determine the potential as well as electric field if electric field and potential are given as a function of x, y, z, or if these functions are vary with the space. Now see the other point related to this. As dv is given as minus e dot dr. So this further we can write e dr cos theta, where theta is the angle between electric field and position vector. Electric field and position vector. It's a very important relation here. Okay, where theta is the angle between electric field and position vector. Now, if theta is your 90 degree, so what I found? That give us dv is equal to 0. dv is equal to 0 means change in potential 0. So v is equal to your constant. This is a very interesting result we are getting here. The V is constant means that indicate. So what is the conclusion from this expression? When we are moving perpendicular, theta is 90, theta 90 means perpendicular to electric field. So that give us when we are moving perpendicular to electric field direction, perpendicular to electric field direction, so potential on those points will be constant. The potential on those points will be same. Those points will be same. It means let electric field here this. If electric field is this, so when we are moving perpendicular to this, it means this. If this angle here 90 here, so when we are moving in this line perpendicular to this, so everywhere on this line, either we are talking about this point or this point or this point or this point, everywhere in all these points, all those points which are in this line will be at same potential. Similarly, if your charge particle, if your point charge is there, due to point charge your electric field this, it is your radially outward we can say. Then what we found here, if we are taking any spherical curve, so all point on this sphere will be also at same potential. So such type of surfaces on which all points are at same potential are called equipotential surface.